So, simulating experiments. This does not substitute for actually doing an experiment. Okay. Yeah, the part of the thing of simulations is you're assuming you know the probability. What it does do is show us what level of random variation we can have with a certain amount of probability. And it allows us to effectively repeat experiments lots of times very quickly. So it shows us when you do an experiment, you get a random sample, right? Ish, or you do a sample study, you get one random sample that falls somewhere within all the possible random samples. If you did all the possible random samples, the mean of those samples would be the actual mean. That kind of makes sense. So what simulating does is shows you how much variation you'd have for a given sample size within your random samples. So it kind of gives you a distribution of possible samples. And what you know, and what we're going to get in chapter 9 is that I have one of these possible samples. Okay. And so simulating becomes a nice tool to just quickly go through and go, okay, well, what would my distribution look like with this kind of sample size? And we can run them really quickly on a calculator, or I'm sure with the right stats software, you could run 10,000 simulations with 5 to 10 minutes of programming. And you're like, okay, that sounds nice. Like 10,000, spit out a distribution for me. Okay, this is what it looks like. Now I have an idea. Oh, that's too wide. I better increase my sample size. Or, hey, that looks great. Even more detailed than I needed. Maybe I don't have to pay for this large of a sample size for my study. Okay. Because as a company, every time you do, the larger your sample size, the more it costs you. So, a girl in the family. We're going to do a basic simulation. And we're going to assume that the probability of the birth of a boy and the birth of a girl is equal. Okay. Um, if you do the actual experimental probability, I think boys are slightly more likely than girls. But boys don't live as long, so because I think this got brought up yesterday, at least in one of my classes. Boys have a shorter life, men have a shorter life expectancy. Yes, because we make dumb choices that get us killed sometimes. There's a 30-foot cliff there. I think I should jump off that on my skis. My dirt, this looks like a great thing to jump off of on my dirt bike. There's probably a place to land it. Into water? I've done that. I did about 70. I did keep my sandals on. So we could simulate a birth with flipping a coin, simulating having 4 kids. You flip a coin 4 times. Heads is boys, tails is girls. What's the likelihood of having a girl? Well, and it's a pretty easy theoretical probability to do, right? You know, one half. Well, the likelihood of not having a girl would be one half to the fourth. So 1 out of 16. So 15 out of 16. But we could simulate it and see, okay, because we know families that don't have 4 kids and no girls, right? It's like, sure, everybody knows that family. Or have 4 kids and no boys. Each of those are only a 1 in 16 chance if it's truly random. But we can simulate it and see the variations. So, steps of a simulation. State the problem or describe the experiment. This one, toss a coin 10 times. What is the likelihood of a run of at least 3 consecutive heads or 3 consecutive tails? Okay. State the assumptions. Heads or tails are equally likely. So we need to state that. We can't just assume that our reader's going to know that heads and tails is equally likely. Okay. We're also assuming that tosses are independent, meaning if you picked it up with heads on top, that doesn't make it more likely to be heads or more likely to be tails. See how, and you're like, oh, these are so obvious. It's hard to realize what your assumptions are sometimes. Okay. Yeah. Like it's sometimes it's just hard to realize, oh yeah, I was assuming that. That seems so obvious. I didn't even think about it. And there will be, I guarantee you on the chapter 5 part of the next test, there will be problems where you're gonna go, well, and you'll make up some weird, really weird reason, and then you'll for what would create bias in an experiment situation or a sampling situation. And then you'll see the answer and go, that was so obvious. And I was making up things that maybe this would be. And that's like a big part of this is just you got to do enough of the problems and look at the answers to go, oh yeah, that's to see the things that are obvious but don't always occur to you. Like, and if you ever do experiments or samples in a business setting or a programming setting or whatever, you have to just get really used to things that cause bias that you don't even think about. And the more you start thinking about it, the more you get there. ANI 2, please keep your voice levels to 1. So then we're going to assign random digits to outcomes. So we look at table B. They chose line 101. You can choose anywhere in there, but we're going to assign 0 through 4 to be, which one do they want? Nope. 1 digit simulates a coin toss. Odd digits represent heads, even tails, is how they chose to do it. It doesn't matter as long as half of them are, you could do 0 through 4 heads, 5 through 9 tails. You could flip that around. As long as there's equally likely. There's really no reason to use more than 1 digit, and I'll show you how to use more than 1 digit. But so we're looking at line 101. So then we simulate it for many repetitions. And we're not going to show you all of the repetitions, but you started at line 101. You would start at some random place. Usually what I would say is if I was using this actually, I'd take my finger, go to put on a line, that's where I start. If I get to the end of the table, I just circle back to the top. And I'll also show you how to do this on your calculator. But, okay, odds are heads, evens are tails. So we do 10. We just take our first 10 numbers and we write them out. Heads, heads, tails, tails, heads, 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 tails, heads, tails. That did have a repetition of 3 heads or 3 tails. So I have 3 heads in a row here in that underlined part. So I mark it as yes. Now I just go from my next numbers, which the table of random digits in the back of the book is subdivided into groups of 5, which is nice when you're doing 10. It's not always nice, but sometimes you have to go across the gaps and things. But it's good because it helps you keep track. Oh, it's easier to keep track of when they're subdivided. So the next ones are 0, 5, 7, 5, 6. It starts with the tails, but then it does 3 heads, which then it does 3 tails, then it does 3 heads. I knew it was yes at after the 4th digit. I didn't really have to write out tails, 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 heads, heads, heads. But I did need to go to the end of those 10 digits before I start my next simulation. Does that make sense? So I cannot start it until that next one, 9. And again, I've got yes after 3 digits. So, hey, 3 out of 3. This is going to happen 100% of the time. No, definitely not. They did a total of 25 repetitions. 23 of them had a run of 3 or more. Kind of high, higher than I would have expected. So if you actually did this, and I think they intentionally chose a set where it was a little high, they chose a starting point. So that's 92% of the time. If you calculated this correctly with using theoretical probabilities, which this would be a pretty hard calculation, you get 82% of the time. 82% of the time, you should expect in flipping a coin 10 times to have a run of 3 in a row that are the same. You just want to do this for the rest of to really test it enough, you'd have to flip a coin until the end of the school year. Sorry, you have to learn other statistics. Coleman's like, I will flip a coin all day to take no more stats tests. I will give us real experimental evidence. The stats is actually highly useful. So assigning random digits. Choose a person that from a group 70% are employed. 1 digit simulates 1 person. So 0 through 6 is employed. 7, 8, 9 is not employed. You could also do 0, 0 through 69, 70 through 99. Gonna give you the same thing. This is what I often do. 0, 1 through 70, 71 through 99, and 00. I'll treat 00 like it's 100. If you need 73% employed, you can do 00 through 72. As soon as we needed 73%, we have to use 2 digits. Okay. No using 1 anymore because you can't get 72% exactly or 73% exactly on that. And they did 73 through 99. Or this is usually the way I do it. And then comma 00 for 100%. That just makes more sense in my brain. I screw it up less, so that's how I do it. We can also do this on a calculator. So I'm just going to clear this all out. No, it's not, it doesn't want to clear. Okay, whatever. So menu, I think this is this under statistics too? No, it's just under probability. Probability random. Random number is a random irrational number. Usually you'll do a random number between 0 and 1. Not terribly useful. Binomial will maybe do something with. Normal would be a random number that would fall within a normal distribution. Pretty much we use random integer. So for this one, I would do 1 to 100. So it's 1 comma 100. And then let's get 10 of them. So when I'm entering this, pretty much the only one I almost ever use, first number. So instead of like the table of random digits where I have to go 00 to 72 or 01 to 9 to 73, and I need a double zero, I can just do 1 to 100. First, last, the comma between them, how many? That makes sense? And I'm sure you did not get exactly the same as I did.
Wait, we did.
Really?
Yeah.
That's strange. I must have,
Yeah, that was.
well, if I hit it again, do you get the same one?
I don't think that's random.
This is not truly. So I didn't know it was, so probably because I opened the program. So, and you guys have never done this, have you?
No.
So what you do, if you noticed when you went to random, they must just have been still set to the same. There's the seed. And if you're doing this on a test or a quiz or if you want to match the program, like a lot of the homework problems will tell you where to start. But one of the tests says use seed, blah, blah, blah. So if I enter random seed 456, it says done. Now if I do that. If you did the same one, you would not get. So all computers and calculators have some sort of, they use a formula to generate randomness, to simulate randomness. And so none are truly random. If you have a really good random number generator, it'll take the time off your computer to the nearest like millisecond and use that as the standard. Now, the calculator intentionally has this enter the seed thing so that I can give you a test and I can tell you, yes, you actually generated, you just didn't just make up 10 numbers that were random. No, you used your calculator to generate it. That makes sense. So I'm guessing the default seed was the same, and this just hadn't been done since my computer or your calculator was reset. So that's how we were getting exactly the same. So was it truly random? No, it was an imitation of random, which works great for me if I want to randomize in class. You know, like it functionally works random, but it's great because all of us will get the exact same random. Or with the table of random digits, yeah, they work great for generating randomness. But in a classroom setting, I want to know, I'm going to tell you where to start. If you're doing your own simulation for some project you're doing in college, you're not going to, you're just going to go through and that's the line I'm starting on. The only reason you would ever, or you'd pick a line ahead of time without looking at it. How about 108? But I usually try to use the finger thing so I can't introduce any accidental bias. That makes sense? So I really like using the calculator over the table of random digits. I want you to know how to use both. If it gives you the choice, usually I'd start at the beginning of a line too. You don't have to though. You could start at the nearest five where your finger is or something. And then make a biased choice from the easiest spot you think from your finger. No, try to be unbiased. Um, you also might have this. Choose one person from a group, 50% are employed, 20% are unemployed, and 30% are not in the labor force, meaning they're either retired or children. That makes sense? Like, yeah, 12-year-olds are not in the labor force. Generally, 80-year-olds are not in the labor force. Also a good thing. I hope not to be in the labor force when I'm 80, if I make it there. It's always an if. But um, yeah, I hope to be retired. And there's a lot of people that, semi-retire, but I would hope to be beyond that by that point. So now we've got a different way of subdividing this. Notice they totally did it a reverse way. Oh, they've got two different assignments. They've got employed, unemployed, not in the labor force, or they just turned it around. As long as the percentages are right, it's totally valid. As long as you tell me what you did. That makes sense? It becomes invalid if I don't have the idea what you did. And it feels like you just made up results. So, frozen yogurt sales. Here's an example of a full simulation. Orders of frozen yogurt have the following relative frequencies: 38% chocolate, 42% vanilla, 20% strawberry. The experiment consists of customers entering the store and ordering yogurt. So somehow they know these percentages, probably from previous use. The task is to simulate 10 frozen yogurt orders. So if 38% are chocolate, we're trying to simulate 10. 0, because this is a two-digit percentage, we need two digits. 0 to 37 corresponds with chocolate. They've assigned 38 to 79 to be vanilla, that's 42% worth, and 80 to 99 to be strawberry. Now, the sequence of random digits begins at the 21st column of row 112 of table B. This is highly intentional to get something that would be weird. So they're beginning in the middle of the line. Do you see where they got to 21st column? So you've gone across the first four groups of five. And so they're starting at that 19352. And 19, 35, 27, you got to go across that gap. 30, 89, 84, 89, 84, 57, 85. Chocolate, 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 Strawberry, 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 vanilla, strawberry. Doesn't look like our percentages at all, does it? Actually, chocolate's pretty on, 40%. Strawberries, 50%. And vanilla was 10%. Strange, huh?
Girl.
You see how you cross that gap, though? That's one of the important things. Um, Also, 3 is 0, 3. If you're looking at the number 3, has to be 0, 3. That makes sense? Don't cut the last ones as 2, 9, 8, 5. That would be biasing your results a lot towards those lower numbers. So in this random simulation, we get very different outcomes than you'd expect. This next simulation, a couple plans to have children until they have a girl, or until they have 4 kids. So they'll stop with girl or they'll stop with 4 kids. So they're doing this simulation. This is how they decided girl, boy for this one. So they started at table 130, line 130. And they just go until they get a girl. So line 130 has 69051. So there's my first 5. We've got boy, boy, and then girl. So we stopped here. Start my next simulation, boy, girl. Boy, girl. The next part is going to be 6, 4, 8, 1, 7. Boy, girl. As soon as we get a girl, we stop. Okay. Now, this simulation, they went until they got one without. You would never stop when you finally get your result. You need to pick how many you're going to do ahead of time. Because otherwise you have massively biased your data.
If I had 30 or like hard that. Just like how many cards are around to get a land?
How many land cards are there? 34. And how many are in the deck? So you could do 00 to 33 as land card, and you could do this repeatedly. You'd probably want to do, you don't want to do until you don't get one in 5 cards or whatever. You want to pick how many am I going to do, and then figure out how many that I don't get out of 5 cards drawn or whatever. Because you could get, oh, I didn't get it on the first one, I'm done. I'm never gonna get this. I'm never gonna get. It's always gonna happen. Well, we know that's not true. They got 13 out of 14, which is close. Theoretical is 15 out of 16. 1/2, 4 times. We'll do theoretical probabilities next chapter, but 15 out of 16, which, so they got close, but that was random. You should never just stop. Hey, we finally got one that's still girls. Don't. So I do a little bit hate that about this example.
If you run out of numbers on a line,
You just go to the next line. You can also, sometimes if you have 3-digit numbers, you'll end up using the first digit from one line and then the next 2 from the next line for your 3-digit number. You just keep going to the next line like there's nothing happened. Okay. Does that make sense for, let's do this one with the calculator. No, that's just giving you commands. Does that kind of make sense for simulations? Like, it's pretty simple, it's pretty straightforward. Again, if you have to repeat these, decide how many you're doing beforehand. Don't let, because otherwise you totally introduce your own bias. Okay, that's it. That's the end of the end of chapter 5.